Okay. So, you notice how we finished chapter 4, and then we're going to take a step back to chapter 3 for just a lecture? That's because I didn't think about putting this lecture on chapter 3, but it kind of makes most sense there and not in chapter 5, to which we will turn in a moment. So I'm backing us up to chapter 3 and tacking on a lecture at the end. 3.7, bridge between state space and output differential equations, and oh yeah, transfer functions. So we learned in chapter 3 we did state space modeling, right? And we had already done input-output differential equation modeling previously, right? We know, I mean, back in the electronics section of this course, we dealt pretty extensively with the input-output differential equation. And we did state space models. We learned how to simulate them, but we didn't really have any discussion of how to go in between these two models. I'm going to teach you how to go one direction, which is from state space model to an input-output differential equation today. And we're going to pass by another system representation. So input-output differential equation is one mathematical model representation. State space model is another mathematical representation of the system. And we're going to pass by one as like on the bridge halfway through in between the two, just to, because we just happen to. We'll get into more detail in the dynamic system dynamics course next semester with this system representation, but it's called the transfer function. So we're going to wave at it as we go by. Okay. It's pretty easy to define, so I figured I'd just define it really quick and then we'd talk about it more later. So the Laplace transform, which we denote with this L operator, L is cool AF. It really is. So back in your differential equations class, you use it to solve differential equations, essentially using forward transforms, Laplace transforms, solving algebraically for the output, and then taking the inverse transform to find the solution. So you could do it all without ever solving a differential equation if you used like a table of transforms, which is pretty nice. But it's also used to define the transfer function h. You know, just another awesome dynamic system representation. For now, we'll use it as a bridge between state space and input-output differential equation representations, merely waving at transfer functions as we pass through. Later, they will be considered extensively, okay? So we'll get there. But first, let's define the transfer function as a system representation. It's really pretty simple. So let a system have an input, u, and an output, y. These don't have to be the only input and the only output, but say we just had one of the inputs, we call it u, one of the outputs, call it y. It might be a single input, single output system, but it might be multiple input, multiple output as well. So let the Laplace transform of each be denoted u and y, so the capital version of them, both functions of a complex Laplace transform variable s. So far, everything is looking familiar from your differential equations class, right? You can take the Laplace transform of a function. It has this Laplace transform variable s in it. It's a complex number. You guys probably talked about that. Definition of the Laplace transform. It's got this integral form with the e to the st in it, all that good stuff. So, yeah, great stuff. And I'm assuming you remember that from differential equations class. Although realistically, there's not a lot to remember for what we need it for in this class, but there's a lot to it, and I hope that you guys review it on your own. So a transfer function, so here's the new thing. A transfer function h is defined as the ratio of the Laplace transform of the output over the input. So simply this. Okay? Pretty easy. That's all it is. So if you take the Laplace transform of a ratio of those two, you have the transfer function. It is exceedingly useful in many types of analysis. One of its most powerful aspects is that it gives us access to thinking about systems as operating on an input and yielding an output. So we think of this transfer function as taking in an input and giving you the output. So we'll talk a lot about this later, but whoa, fat marker. Gets me every time. Okay, so you have an input that goes into your system that we're representing with a transfer function, okay? So h, and then out of that comes y. I mean, we could think of this in the Laplace transform version of the input and the Laplace transform version of the output too. Either way of thinking is fine. But we have an input go in, the transfer function operates on it, and we get an output out. Okay? And that is pretty apparent when you see that if you rearrange this equation up here, we have that y of s equals h of s u of s. So h operates on u and gives us y. So that's the way that we think about it. And that's really all that we're going to do with the concept of a transfer function for now. We're just going to use that, and then what we're going to do is we're going to bridge both the input-output differential equation representation of a system and the state space model representation of a system to the transfer function, and then we'll be able to go in between the state space. Well, our goal is to be able to go from state space to differential equation, and so we're going to just stop by the transfer function on the way. Okay? Oh man, I didn't fix that reference, so I didn't know. Playtech can't find the reference that you stick in. It sticks in question marks. So I forgot to rename the label when I brought it in. In any case, I'll fix that. Laplace transform of, so what this is the input-output differential equation. Yields something interesting, assuming zero initial conditions. So, thank God I brought my notes. There's a lot to write here. This big blank spot is going to get really filled. So we take the Laplace transform. So the left and right hand sides of this are essentially the derivatives, time derivatives of the output on the one side. Like if it's a first order system, we would be like tau dy dt equals something with u's on the other side, right? So input-output differential equation. So the Laplace transform of, well, I'm going to use parentheses instead of the squiggly one, but the nth time derivative of y dtn plus, I'm going to give a little bit of space here because I'm trying to align these. We'll see how that goes. an minus 1. So I made the first coefficient 1 as usual. The second coefficient is an minus 1 times the n minus 1th, n minus first derivative. I don't really know how you would say that. N minus first derivative of y with respect to time plus all the way down to a1 dy dt, so down to the first derivative of y with respect to t, plus a0, so the 0th derivative of y with respect to t is just y. So that's the left-hand side. So we're going to take the Laplace transform of the left-hand side of the input-output differential equation. The right-hand side of the input-output differential equation is, we're also going to take the Laplace transform of it. So I'm going to give ourselves a little bit more space because there is a coefficient here. So b m and then d m u d t m, which is the mth time derivative of the input, plus b m minus 1 and the m minus first derivative of the input, plus b1 du dt plus b0 u. Okay, so what's in here is, of course, the left-hand side of just an input-output differential equation, right? A bunch of time derivatives of the output. So for the first-order system, all this stuff isn't there, and we just have a first derivative. But we want to be able to do this in general. So an nth-order system can be written like this, and the right-hand side is going to have time derivatives as well of the input. Oftentimes, we don't have any time derivatives of the input, and we just have some input function over here. But in general, you can have time derivatives of it as well, so we're going to do this in general. So take the Laplace transform of each side. Now, one of the properties of the Laplace transform is that it distributes in. So it's a linear operator. So remember, it's just an integral, right? So take the integral, and all of its properties come from the integral. So if you take the integral of a sum of a bunch of terms, you can just take the integral of each term and sum the results, right? Mm-hmm. So we're going to use that. Also, if you have a constant multiplying something inside the integral, you could pull that constant out, right? So Laplace transform, it also applies to the Laplace transform. So we can pull out all the coefficients. So when we do this, we're going to take the Laplace transform of each term, and then we're actually, all these constants can be pulled out of each term as well. So what we have on the left-hand side is the Laplace transform of dn y dtn plus the Laplace transform, oh wait, we got at the end, the an1, n minus 1, we're going to pull that out first. And we're going to have the Laplace transform of dn minus 1 y dtn minus 1 plus a1 Laplace transform of dy dt plus a0 Laplace transform of y. Whew. So that's the left-hand side, right? The right-hand side is going to look very similar. We're going to distribute the Laplace transform on the right-hand side as well. So we have a bm Laplace transform of dm u dtm plus bm minus 1 times the Laplace transform of dm minus 1 u, this is weird looking u, divided by dt m minus 1, weird looking u. B1 times the Laplace transform of du dt plus, this last one doesn't, so b0 and the Laplace transform of u. Okay. Whew. It's just a lot of writing, but like the concept's pretty straightforward, right? Let you guys catch up. Okay, so what do we do now? We have these Laplace transforms of a bunch of time derivatives, right? So we said before, we turned the page, that we're going to assume the initial conditions are 0. Do you remember the Laplace transform property of what happens if you take the Laplace transform of a derivative? It's a good one. It's actually like one of the key things that you did to solve differential equations with Laplace transforms. But it was that you take the order of the derivative and you multiply the Laplace transform of the function that is the derivative is of by s raised to that power, right? Also, these initial conditions that come in, those terms for each of them, but we're going to just say, assuming 0 initial conditions. So all your initial conditions are 0, in which case all that gets swept under the rug, and this becomes, so Laplace transform of y, we typically just write capital Y, right? Laplace transform of u, we typically just write capital U. So I'm going to just switch over to that notation on this next line. So this Laplace transform is s raised to the nth power. So s being the Laplace transform variable s, that complex variable. S raised to the nth power times the Laplace transform of y, which we're just going to say is y, capital Y, right? And just because I don't want to keep writing of s in every damn term, I'm just going to suppress that in the notation. So s to the n y plus a n minus 1, s to the n minus 1 y plus, notice how much more compact this is getting, a 1 s to the 1, right? So just s, y, plus a 0, and s to the 0 is just 1, so we just say y. Equals, on the right-hand side, we have bm s to the m, Laplace transform of the input, u, plus bm minus 1 s to the m minus 1 u plus b1 s to the 1, so just s, u, and finally b0 times s to the 0 u. So just that. And holy crap, look at how edited that was. Holy crap, you can factor out a y from every term on the left-hand side. And on the right-hand side, you can factor out a u from every term. Awesome. So that means that we can solve for, you guessed it, y over u. But we're going to do 2 steps. We'll do 2 steps. Okay, so what we're going to do is we're going to say, okay, let's factor out y from the left-hand side and factor out u from the right-hand side and divide whatever over on the left-hand side is not y over to the other side. Okay, so it's a little hard to say in words. So solving for y, that's why we use equations. So y, I'm not going to use the, I will because there's only 2 of them. Y of s equals big fraction. So I always feel like I always shortchange by fraction, so I'll just make it super long. U of s. Okay, so I got to write this ratio. So on the left-hand side, you factor out all this stuff. On the right-hand side, you factor out all this other stuff. We'll do the right-hand side first because it's the numerator. So factor out u from the right-hand side, and we get bm s to the m plus bm minus 1 s to the m minus 1 plus b1 s to the 1, or just s, plus b0. So that is the right-hand side with u factored out, which u is factored out, so that's good. And then the left-hand side we factor out, so the first coefficient is just 1 s to the n. I'll move it over a little because we want to align it. S to the n. The second term is a n minus 1 s to the n minus 1 plus a1 s to the 1, or just s, plus a 0. Okay. So now, I don't know about you guys, but I feel like solving for y over s, which is our transfer function, is going to be pretty easy at this point. We'll divide both sides by u, and we're done. Right. So that's awesome. So the inverse Laplace transform of y, so before we do that, is the steady state solution to the system. So that's pretty cool. I I'm thinking. Time out. It's not the steady state solution. It is the what we have called the forced response. Forced response, which is to say the response of the system to an initial or to an input with initial conditions all set to 0. So yeah, that's why you don't write notes at 2:30 in the morning. It's just a heads up. However, this is not our primary concern. Rather, we're interested to solve for the transfer function h as a ratio of y over u. So, of course, as we know, h is defined as being y over u, and therefore, we just solve this just for y over u, y divided by u, bring u over. You're just left with this ratio right here, right? That's what you're left with as being h. Exactly the reverse procedure. So okay. This is the transfer function for an input-output differential equation. So this is the definition, and this is the expression if you have an input-output differential equation. Okay? Now, exactly the reverse procedure, then, can be used to convert a given transfer function to an input-output differential equation. So you can essentially just do this in reverse. Notice that actually you don't have to go through this every time, because you can look at the initial input-output differential equation and say, oh, on the right-hand side, I just put in all the coefficients and take s raised to the power of the time derivative, and then the left-hand side, I just essentially transcribed the denominator with all of its coefficients and its powers associated with the time derivative order. So this procedure is fairly straightforward to do the one direction. You can also do it the other direction. Okay, so you can say, oh, here's a transfer function. Let's look at a differential equation. Essentially, all of so s to the n is then going to be the nth time derivative of y on the left-hand side, and etc. So you can do this either way. It's pretty straightforward to just go back and forth with this procedure. So yeah, that's how to find the transfer function from an input-output differential equation. And then you can also go from an input-output differential equation, or from a transfer function to an input-output differential equation with this method, this procedure. So now, okay, so what we've got, remember, we've got three system representations we're talking about today. We've got state space, we've got the transfer function, transfor, and we have the input-output differential equation representation. So three representations for a system, mathematical representations for a system, and these are these are three of the four most important. Okay, so almost seen all of the most important mathematical models now. So I'm not going to. So we want to be able to go from a state space model to an input-output differential equation. So what we just learned how to do is to do this input-output differential equation to transfer function. What I said is you can go from a transfer function to an input-output differential equation very straightforwardly. It is essentially exactly the same procedure, just in reverse. Okay, so it's kind of too tedious to go through both directions because it's just kind of annoying. But in an example, we'll probably talk about how to do this. But I think it's fairly obvious from the procedure. So we've learned this, how to go from this to this or that to that. What we're now going to do is learn how to go from this to this, from state space to transfer function, which will allow us to do what we want to be able to do, I guess, for the remainder of the semester. One of the procedures we're going to want to be able to do is to go from state space to transfer function to input-output differential equation. Okay? So, and the primary motivation for that at this point is that we know how, it's a good thing to know how to do, right? But the input-output differential equation, we know how to solve that analytically, okay? That's our main motivation for doing it, for learning how to do this bridge right now. It's the input-output differential equation we know how to solve using, method of undetermined coefficients. We know how to solve state space models in MATLAB. We learned how to do that, right? Just simulate it. But that doesn't give us a lot of insight into certain types of systems and their characteristics. And we're going to want to talk about those a little bit. So that procedure of using MATLAB state space to simulate doesn't give us those insights. So we want to be able to take a state space model and make an input-output differential equation to do some analysis on different types of systems and their properties for the remainder of the term. So the next couple lectures are going to be on that. But I want to be able to take the state space model, write it as an IO differential equation first, so that we know how to sort of go from our cool system models and state space to an IO differential equation to a solution analytically. Now, there is also a way to go from a transfer function to state space, okay? Or from an IO differential equation directly to state space. There are these procedures here, but we're not going to consider these in this class. They're not unique, okay? So if you have a state space model, you can come up with the input-output differential equations, transfer functions, and those are unique representations. There's one answer for those questions. An IO differential equation or a transfer function can be written as a state space model, but the variables that you choose for your state variables determine what that looks like, and you lose information. We don't know enough about state space yet. We haven't learned enough about it yet to understand why that's true. But you lose some information if you go from a transfer function or IO differential equation to state space. So if you did, so I shouldn't say that. You don't lose any information if you go from IO differential equation or transfer function to state space. But you do if you go from state space to one of these, you lose information. So you go from state space to these, and then back, you've lost something, okay? So state space is kind of like the high fidelity model right here. So this is like the hi-fi right here. High fidelity model of the system. This is the gold standard type of model. These ones are also really good, really effective. State space wasn't developed until later, by far. So these other ones were around for quite a while before state space was developed. And so this is actually like the really great way to represent a system. But there's still a lot of really cool things you can do with these other representations as well. So if you go from this high fidelity and you compress it down to a transfer function and an IO differential equation, just like a JPEG from a TIFF, if you're into images, or if you went from FLAC to an MP3, compress it down, you try to go back, you're going to lose some information, right? Some information's gone. It's compressed. It's lossy. I don't know. Are these working for you? These analogs? Anyways. Okay, so let's learn. So we learned about how to do this bridge here, transfer function IO and back. Let's do state space to transfer function now. So we're going to focus on this guy right here for the next subsection here. So bridging transfer functions and state space models. Given a system in the standard form of a state equation, which is, dx dt equals ax plus bu, our old friend, we take the Laplace transform. There it is again. Oh, man, it's the best. Laplace transform. Oh, you're cool. Okay, so we will take the Laplace transform to yield, assuming zero initial conditions again. Remember, we're going to do assuming zero initial conditions. We'll justify that more later why we do this, assuming zero initial conditions. So in this matrix equation, this vector equation, taking the Laplace transform, I didn't change the symbols. I should have gone to capital X's, so this should be S capital X vector equals a capital X vector, just to denote this as the Laplace transform. It's essentially the same, but these are now Laplace transform variables. So the time derivative, there's only a first time derivative, so s to the 1, okay, x, and then we can solve this for x. It's a matrix equation, but a little pretty basic linear algebra gives us the solution for x, which is that x, once again, capital X and capital U, is equal to SI minus A inverse. So I here is the identity matrix. So I say it right there, identity matrix with the same dimension as that of A. So you have to do that algebraically. There's kind of we could have a discussion about that, but in linear algebra you might be familiar with this procedure. The identity matrix, for those of you who are maybe unfamiliar with that, is the matrix that has 1s all along the diagonal and 0s everywhere else. Okay? If you multiply any matrix by the identity matrix, you get back the matrix, the original matrix. It's essentially the matrix version of 1, right? So for a scalar, if you multiply anything by 1, any scalar by 1, you get back the scalar you had. If you multiply any matrix by the identity matrix, you get back the original matrix. Okay. The standard, so when you multiply S, the Laplace transform variable, by I, so this is SI minus A. So you just essentially stick S in here all along the diagonal, right? It's just element-wise multiplication of S. S times 0 is still 0. S times 1 is S, so you get S's along the diagonal, and 0's everywhere else. So you have to do that. You have to do this matrix subtraction. Then you have to do a matrix inverse, which is definitely the hardest linear algebra thing that I'm going to require of you this term, is taking a matrix inverse. But by hand, I only expect you to be able to do up to a 2 by 2. I mean, 3 by 3 would be good. Let's say by hand you should be able to do up to a 3 by 3, but it's unlikely to see that on a final exam in class because, hey, I don't want you to spend all your time inverting a matrix. So probably 2 by 2 is most likely. Or 1 by 1. It's also possible. So, yeah, okay. Yes?
Do you care if we just throw that in our T84 and invert it that way?
I do not care, although keep in mind that your TI-84 probably can't do a matrix inverse if it's symbolic.
Oh, gotcha.
So that's the gotcha part. Yeah, so if your matrix inverse calculator function can handle the symbolic version, then great. But I don't know that it can. I kind of think it's only numerical. So keep that in mind. So MATLAB can do a symbolic matrix inverse. So can Mathematica. So can Python. Pretty much any software package can. But I don't know that calculators can do it. I've never seen one that can.
The really fancy ones can.
I'm sure. Yeah, that would make sense. I used to have a TI, like the one that looked like a computer, had like a full keyboard. That was nice. I still have it. I just don't think it's had a battery that's worked in 10 years. Because I moved over to the computer-based stuff almost exclusively. All right, let's keep it rolling here. So we've got this solution for x. Okay. X, the relationship between x and u. I mean, we actually have found the transfer function between the input u and if we considered the state vector to be the output, and then it would be the output x. But we usually don't consider the state variables to be the output, right? We have a whole other equation for the outputs, the y equals cx plus du equation. So the standard form of the output equation yields the output solution y equals, so once again, these probably should be capital, y equals hu, where we define the matrix transfer function h, I know, same symbol, but that's typical to use, to be c times si minus a inverse b plus d. Okay, so this is h. So this is a whole matrix, though. Okay, this isn't just a single transfer function. So the element hij is a transfer function from the jth input to the ith output. Okay. So if you have a multiple input, multiple output system. So remember in the motor analysis we've been doing, and we had that set up with the torque source, like the brake, and the voltage source, so two inputs. And we had like, I don't even remember how many outputs, like 12 or something like that, a lot of outputs, right? So there's a transfer function that can be defined from each input to each output. So if there are, we typically say R inputs, and there are M outputs, there are R times M transfer functions. If there's only one input and one output to a system, which is actually probably the most common case, you have one input, one output, it's just a scalar and there's only one transfer function from that input to that output. But in general, we have this nice relationship. So we can find the transfer function from any input to any output, literally with this one equation, 3.9, which is, I mean, pretty awesome. I mean, this is the power of linear algebra. This is why people use it. We don't use it just because it's harder. We use it because it's really helpful to condense a lot of analysis down into simpler mathematical objects. So instead of a whole bunch of equations, we have one equation. It's a vector equation. And then the expressions we can use and the solution techniques we can use can be sort of condensed into just one instead of many. So it's really, it's pretty nice. So this is the solution. So if you have your A, B, C, and D matrices, you can define the transfer function from any input to any output just with this expression, which is pretty great. So this is super powerful, 3.9. We're going to keep coming back to that. But for now, we're just interested in the fact that we were able to do this. So, good. So as I mentioned, the reverse procedure of deriving a state space model from a transfer function is what is called a state space realization, which is not a unique operation. There are several different realizations for a single transfer function, and it's not considered here. So back to our little diagram. We now know how to go from state space to transfer function, right? So if I had to write in the way we do that, we would say C times SI minus A inverse B plus D. And how do I remember that equation? Well, I use it a lot. And then also, this is just, so remember we solved this first one for x, and this was the solution for x, right? Boom. Well, the way that I derived this 3.8 equation is just by plugging into, in terms of Laplace transform, y equals cx plus du. So all I did was plug in this solution for x into x here. So the c times whatever that solution was plus d, and then there's a u in both. You factor out the u. So that's why I end up with this expression. That's also why I can remember it, because this is just cx plus du. So x and then plus d, and then both of these are multiplied by u. So that's why I can remember it off the top of my head. I mean that, and I'm super genius, but I'm not. Okay, so good. So now we know how to go from state space to transfer function. We know how to go from transfer function to IO differential equation by essentially just interpreting the s to the n, s to the k just being the kth time derivative of either the input or the output. Okay? Okay. I know. So much fun. So much fun. Okay, any questions on this before we move on? I think I might have time to do the next one. We'll see. I got it. There's only one page. Any question? Okay.